Modern maritime navigation operates under a paradox. While wind and wave patterns are now predictable with high reliability, forecasting the movement of ocean surface currents remains a persistent operational blind spot. Even with advanced software, a massive cargo vessel can find itself pushed miles off its calculated course by unseen forces in the water. This chart shows the results of a recent industry survey, where 70% of maritime captains rated their ocean current forecasts as average or poor. The industry operates with high confidence in its atmospheric data, but views the ocean itself as an unreliable variable. When a ship encounters an unmapped adverse current, the crew must make constant reactive adjustments to engine speed to stay on schedule. Navigators measure progress in two ways: speed through water, which is the raw mechanical effort generated by the engine, and speed over ground, which is the vessel's actual progress towards its destination. When an adverse surface current pushes against the hull, speed over ground drops. To maintain the ETA, captains are forced to ramp up their speed through water, burning significantly more fuel to cover the exact same distance. These unpredictable surface currents create a massive, systemic leak in global shipping fuel efficiency. The International Maritime Organization's Carbon Intensity Index now mandates that vessels operate at slower speeds to reduce total emissions. Implementing this directive across a global logistics network requires extreme operational precision. Physics dictates that at slower engine speeds, the relative drag of an adverse current exerts an exponentially heavier penalty on the vessel's total transit time. To manage these tighter margins, the industry is seeking alternatives to the traditional numerical modeling that has defined weather forecasting for decades. The startup Amphitrite, utilizing NVIDIA's AI infrastructure, is testing a different approach, treating the ocean surface as a computer vision problem rather than a three-dimensional physical simulation. Reaching maritime decarbonization goals requires the industry to change how it analyzes surface data. Weather forecasting traditionally relies on computational fluid dynamics, or CFD. These models divide the atmosphere into a grid, calculating the air physics inside each node. This diagram shows a 1,000-kilometer-wide atmospheric storm system. Because of its scale, the event is easily captured by a standard computational grid. Oceanic eddies are 10 times smaller, averaging only 100 kilometers across. These high-energy systems can slip between the nodes without being detected. Because the open ocean lacks a dense network of physical sensors, these numerical models are often initialized with sparse, incomplete data. This North Atlantic map plots two diverging current vectors. Leading models, Copernicus and NOAA, place the exact same currents in completely different locations. These discrepancies misplace main current veins along major shipping lanes, like the route between the US and Europe. Traditional numerical models struggle because they apply a low-resolution atmospheric tool to a high-resolution oceanic problem. Amphitrite's approach treats the prediction of surface currents as a two-dimensional image processing task. Instead of relying on sparse physical sensors in the water, the system ingests vast data collected from orbit. This diagram visualizes the first raw input, a data plane tracking chlorophyll imagery, revealing how biological material moves. A second essential layer is added, sea surface temperature. Finally, the network integrates high-resolution radar altimetry from missions like SWAT to track sea surface height. A deep learning neural network ingests these non-linear satellite images to identify the hidden dynamics connecting them. The output is the HIRES-Currents model, which compresses these layered inputs into a unified map of the surface. This fusion achieves a 1/30th degree resolution, mapping the ocean down to a 3-kilometer scale. When validated against 100,000 real-world drifter measurement points, the model reached 89% accuracy, compared to the 62% accuracy of standard models. Deep learning transforms sparse, multimodal satellite telemetry into a highly mathematically precise map of the ocean's surface dynamics. Maintaining this global forecast requires the computational capacity to process thousands of satellite images continuously. Amphitrite utilizes NVIDIA's Earth-2 platform and the ForecastNet architecture to manage this workload. GPU-accelerated computing handles the parallel processing of these satellite time series observations at speeds far beyond CPU-driven systems. Advanced AI infrastructure provides the immense processing capacity required to turn historical satellite data into real-time routing intelligence. High-resolution data directly impacts the physical performance of a vessel attempting to maintain its ETA. This graph reveals how delays stack up when a vessel traveling at lower speeds hits an unpredicted adverse current. Because a slower ship spends more time fighting opposing water, it loses its fuel efficiency in this specific zone. Access to 3-kilometer resolution lets ships navigate the edges of oceanic eddies and leverage favorable currents. High-fidelity AI data mitigates the physical delays that occur under slow-steaming mandates. On Mediterranean routes, shipping companies using this AI data achieved a 10% reduction in carbon emissions. Navigating against unmapped forces is now being replaced by the ability to calculate a course at 3-kilometer resolution. Through the Ocean Bulletin platform, maritime captains now have continuous access to high-fidelity navigational intelligence directly on the bridge. This technology is deployed to support green digital shipping corridors, including routes between Singapore and Rotterdam. Alternative fuels are only one component of the maritime industry's net-zero transition. The other is mastering the ocean's non-linear dynamics through deep learning.